Hello everyone and welcome back to Statistics 1. Here is Jonathan. So in this lecture, I'd like to talk about probability function. So let's start by the notation. Let A be an event in omega, meaning a subset. Now, TA denotes the probability that the event A will occur. Now, if you think about it, when we started talking about probability last time, we said that in general, you should think about probability as a machine, okay, denoted as P, where the input is an event. So here the event is denoted as A. And now the machine is going to return a numerical value. And this numerical value is denoted as PA, the probability that the event will occur. Okay, and here we start with the definition. Definition of probability function. Definition says that, suppose that we have a sample space, let omega be a sample space. The probability function on omega is a function such that for all the events, for all the events in omega, the probability of A is a real number holding the following axioms. Okay, now there are three axioms, and let me present them. First, the probability of A will always be non-negative, bigger than or equals to 0. Okay, why we say non-negative and not positive? Because it includes 0. Okay, so the probability of A is always non-negative for all events A in the sample space omega. The second axiom says that the probability of the sample space is always 1. Okay, and the last one says that for any two disjoint events A and B, the probability of A union B equals to the probability of A plus the probability of B. So basically, those are three axioms. So think about axiom as rules that we need to accept from the beginning. Okay, we are not asking why they're true, but only accepting those rules. Okay, and by the way, there is some intuition in those rules. So think about it. Saying that the probability of omega equals to 1, it means that if you are rolling a die, the probability to get 1 or 2 or 3 or 4 or 5 or 6, that needs to be 1, okay? Because you know that one of those outcomes is one of the results that you are going to get. And therefore, it's kind of intuitive why 2 needs to be an axiom. And also, the probability of A needs to be non-negative. So we can't really talk about probability, that negative probability. And the last one is it comes from the idea that if you compute the probability of two disjoint events, disjoint, let me remind you that that means that A and B are not sharing any elements. So in this case, it's exactly the same as computing the probability of A plus the probability of B. Okay, so you can split this probability into 2 and them both. So that's basically the idea. We don't really need to explain why those axioms are true. The only thing is that we need to accept them. Okay, and now I'm going to use those axioms in order to prove some different theorems, basic theorems in probabilities. So that's what I'm going to do now. Okay, so let's start by proving the first property, saying that the probability of the complement of A, that's exactly 1 minus the probability of A. Now, let's try to understand intuitively why it's true, and then we'll prove that. Okay, so first, let's use the Venn diagram. Okay, now that's the sample space. Here is A. And we said that the complement of A is all the elements that are not part of A, but still in the sample space. So here is the complement of A. Now, we want to show that in order to compute the probability of the complement of A, what do we need to do? We need to take 1 minus the probability of A. But if you think about it, it means that you are going to take all the sample space and subtract the area of A. And that's exactly the complement of A. So in the end, there is an intuition, this formula, okay, this property, and you can understand it by using the Venn diagram. But I'd like to show you the proof, how we prove those kinds of properties. Okay, so let's see the proof. So first of all, I hope that you remember that if we take A union the complement of A, in the end we need to get omega. Therefore, if I ask you what is the probability of omega, it's equivalent to asking the question what is the probability of A union A, complement of A. Okay, but the probability of omega according to axiom 2 equals to 1. And also you know that A and complement of A are disjoint events, and therefore according to axiom 3, you can separate them into 2, probability of A plus the probability of the complement of A. Meaning that 1 equals to that, equals to that, equals to that. So from here we get that 1 equals to the probability of A plus the probability of complement of A. Now by using algebra, we get that the probability of complement of A equals to 1 minus the probability of A. And that's exactly what we needed to prove. Let's continue with the second property. Second property says that the probability of the empty set is 0. By the way, here the intuition says that what is the probability that in case that you're doing an experiment, nothing is going to happen? Of course, it's 0. I mean, if you're doing an experiment, you're going to get one of the outcomes. Right, so that's basically the intuition. But, of course, again, we need to prove that. So here's the proof. First, we know that the probability of the empty set equals to 1 minus the probability of the complement of the empty set. Why? That's exactly property 1 that we proved. Then we remember that the complement of the empty set, that's exactly omega, the sample space. But according to axiom 2, we know that the probability of omega is exactly 1. So what do we get? 1 minus 1 equals to 0. So from here we get that probability of the empty set equals to 0. Therefore, the probability of the empty set equals to 0. And that's all. Now let's continue with property number 3. We need to prove that if A is a subset of B, then the probability of A needs to be less than or equal to the probability of B. Now I'd like to explain the intuition by using again the Venn diagram. Here's the Venn diagram. Now A is a subset of B. That means that you have two events, A and B. Here is, of course, the sample space. Now, according to the property, if A is a subset of B, then the probability of A is less than or equal to the probability of B. That means that the area of A needs to be less than or equal to the probability of B. And of course, we can see that from the Venn diagram. And now here's the question. How do we prove that? So here's the proof. So first, we want to write B, the event B, differently. So we want to write B as a union of two disjoint events. And the idea is that we are going to use axiom number 3. Okay, so let's see how exactly we can write B by union of two disjoint events. So the idea is that we are going to take this part, the green area, and then we can add to it the red area, and in the end, that's exactly B. Okay, so let's see how we can write that. So first of all, we are going to take A, the red area, and we are going to add to that B and not A. Think about it. B and not A. B and not A, that's exactly the green area. Okay, so that's the green area. And here is the red area. So if you add those two, you'll get exactly B. So the probability of B exactly equals to the probability of A union B and not A. Now, axiom 3 says that in case that those two are disjoint, so you can just use the Venn diagram and see that the green area and the red area are two disjoint areas, and therefore we can split it into two. So that becomes the probability of A plus the probability of B and not A. Great. Now, let's use the other axioms. First, please notice that the probability of A is always bigger than or equals to A. And also the probability of B and the complement of A is always non-negative. That comes from axiom 3. So if we add those both inequalities, we'll get that the probability of A plus the probability of B and not A needs to be at least 0 plus the probability of A, meaning the probability of A. So in the end, the probability of A plus the probability of B and not A meaning the complement of A, needs to be at least the probability of A. And that's exactly what we need to write here. That needs to be at least the probability of A. Why? That's the explanation. Okay, so let's see what we got from here. So first, the probability of B equals bigger than or equals to the probability of A. That means the probability of B is bigger than or equals to the probability of A. And that's exactly what we needed to prove, because here we need to prove that the probability of B is bigger than or equals to the probability of A. And that's exactly what we showed here. And that's all. Okay, next property. We need to prove that the probability of any event needs to be at most, meaning less than or equals to 1, for all A in sample space, meaning omega. Okay, so here's the proof. So first, I hope that you notice here that A is always a subset of omega. Any event is a subset of omega. By the way, that comes from the definition itself. Now, that means that according to property 3, the probability of A needs to be less than or equals to the probability of omega. But the probability of omega, according to axiom 2, equals to 1. That means the probability of A is less than or equals to 1. And that's all. From here, please notice that from now on, we know that the probability of any event needs to be at least 0, meaning non-negative, but at most 1. Okay? This part comes from axiom 1. And this part comes from property 4. The next property is intuitive, but is a bit more complicated to prove. So let me show you what we need to prove, and let me explain the intuition. And then we are going to prove that. Okay? So prove that for any two events, A and B, in omega sample space, the probability of A union B equals to the probability of A plus the probability of B minus the probability of the intersection of A and B. So let me show you why it's true. The intuition itself. Okay, so let's say that we have A and B. That looks like that. Here is A, here is B. So according to this property, if we want to compute the probability of A union B, what we need to do is to take A, add to it B, and in the end, because we added the middle part twice, we need to subtract it one time. Okay, so that's basically the idea. That's what the property says. Now we need to prove that. So here's the proof. Okay, so first, I'd like to understand how exactly we can write the probability of A union B, okay, in a way that the two events are going to be disjoint. Okay, so let's see. The probability of A union B. What we can do is to take all of A and had to hit what exactly? So let me just draw another Venn diagram so it's going to be much easier to understand that. Okay? So again, so we have A, we have B. Okay, so we are going to take all of A, all of A, and I want to add this spot, the red area here. So what is the red area? How exactly we can write it explicitly? So we're going to write it as B and not A. Think about it. That's exactly what the red area represents. B, but not the element that might be in A. Okay? So if you just look at the Venn diagram here, I hope that you notice that those two are disjoint. And if those two are disjoint, that means that according to axiom 3, we can split them. Probability of A plus the probability of B and not A. So now, hopefully, in the end, we need to get the probability of B and not A equals to the probability of B minus the probability of A and B, because if you think about it, that's the last part here that we need in order to prove that. Okay, so how exactly from here we need to continue? So let's see. Let's look at B. I'd like to write the event B, again, in a way that it's the union of two disjointed events. So again, let me draw a Venn diagram, A and B. How exactly we can write B as union of two disjointed events? Okay, so let's see. First, we can take the intersection, and then we can head to it this part, the blue area. So we can write B as A and B, the intersection, union B and not A. That's exactly B and not A. Okay, that means that the probability of B equals to the probability of A and B, union B and not A. But a few seconds ago, we said that those two are disjoint. That means that we can split it into two, according to axiom 3 again. So that becomes the probability of A and B, plus the probability of B and not A. Great. That means that the probability of B equals to the probability of B and A, plus the probability of B and not A. So let me write it. So from here, the probability of B equals to the probability of A and B, plus the probability of B and not A, the complement of A. And you can use algebra here and get that the probability of B and not A equals to the probability of B minus the probability of A and B. Great. So now that we get this formula, we can write it instead of that. We are going to replace the probability of B and not A with this formula. So let me write it. So we get from here the probability of A plus the probability of B minus the intersection. So from here we get that the probability of A union B equals to the probability of A plus the probability of B minus the intersection. And that's exactly what we needed to prove. And that's all. Now maybe some of you might ask themselves if property number 5 contradicts axiom 3, because if you just write here axiom 3 according to axiom 3, the probability of A union B needs to be the probability of A plus the probability of B. But according to property 5, we said that the probability of A union B equals to the probability of A plus the probability of B minus the intersection. So maybe some of you ask themselves, so maybe there's a contradiction between the axioms and the property that we just proved. So the answer is there's no contradiction between those two, because axiom 3 says that this is true only if A and B are disjoint. Now let's see. If A and B are disjoint, according to property 5, the intersection needs to be 0, because if A and B are disjoint, that means that the intersection is the antiset. And one of the properties that we proved says that the probability of the antiset is 0. And from here we get exactly the axiom 3. Therefore, there is no contradiction between axiom 3 and property 5. Okay, now there are two more properties I'd like to talk about without even proving them. Okay, so property 6 says that the probability of not A, the complement of A and B, equals to the probability of B minus the intersection. So let me just explain the intuition. The intuition says that if we use the Venn diagram, okay, we draw A and B. So the probability of B and not A, that's exactly the red part here. That equals to all of B minus the intersection. So if you take all of B and you subtract the middle part of the intersection, you'll get exactly the red part. So that's property 6. We won't prove that. Exactly the same for property number 7. Property number 7 says if you want to compute the probability of A and not B, that's exactly the probability of A minus the probability of the intersection. Let me draw again a Venn diagram. Okay, so here is A, here is B. And now, what do I mean by A and not B? A and not B, that's exactly this red area. A and not B. Do not touch B. Okay, great. That's exactly taking A, all of A, including the middle part, and subtract the intersection. Okay, so that's basically the intuition of those two properties. And that's all for the properties. So we covered the 7 properties that we are going to use in class. And now, I'd like to give you an example to understand how exactly we can use those properties in order to solve questions. Okay, so here's the example. An investor buys 2 stocks. With probability 0.6, the first stock will rise. With probability 0.7, the second stock will rise. And with probability 0.1, the 2 stocks won't rise. Hey, what is the probability that at least one stock will rise? So here is how we solve those types of questions. So first, we need to denote all the different events. So we can denote A as the first stock will rise. B, the second stock will rise. Now, by using those notations, we can write that the probability of A, that's 0.6. The probability of B is 0.7. And now here, last one, with probability 0.1, the two stocks won't rise. Saying that the two stocks won't rise, that's exactly saying that the probability of not A, the first stock, won't rise, and also the second one won't rise, and that's exactly 0.1. Okay, now we need to understand what we need to answer here. What is the probability that at least one stock will rise? At least one, it means that all the first one, all the second one, or maybe both of them. And that's exactly the union, because the union represents exactly that, or A, or B, or both of them. So the question here is, what is the probability of A union B? So that's the question. Okay, now, notice that, according to the question, we know that 0.1 equals the probability of complement of A and the complement of B. Now, one of the De Morgan laws says that, De Morgan law says that that equals the probability of A union B, the complement of that. Now, according to one of the properties that we mentioned in class, the moment that you have the probability of the complement of an event, that's exactly 1 minus the probability of the event itself. So that's exactly 1 minus the probability of A union B. So what do we have here? 0.1 equals to that. So 0.1 equals to 1 minus the probability of A union B. From here, we understand that the probability of A union B needs to be 0.9. Okay, let's continue with B. What is the probability that the two stocks will rise? Okay, so we use the same solution as before, the same notations. And here's the information, and also from section A, we know that the probability of A union B equals to 0.9. So we need to ask ourselves, what do we need to compute in here? So saying that the two stocks will rise, it means that we want to compute the probability that the first one will rise, A, and also the second one, B. That's the question. Now, according to one of the properties that we saw in class, we said that the probability of A union B equals the probability of A plus the probability of B minus the intersection. Another way to write that is that, by using algebra, is that the probability of A and B equals the probability of A plus the probability of B minus the probability of A union B. Now let's see. The probability of A is given to us, it's 0.6. Also the probability of B is given to us, 0.7. And from section A, we already computed the probability of A union B, that's exactly 0.9. So now, if you plug all those numbers and you compute the intersection, you'll get that that's exactly 0.4. Okay, great. So now we continue with C. What is the probability that exactly one stock will rise? So again, we use same notations, but now we also have the probability of the union 0.9, and from the previous section, we have also the intersection. So what do we mean by exactly 1? Exactly 1 means that the first rise, but not the second one. That's one option. Or the first one didn't rise, but the second one rise. So that's exactly what we need to compute. Now, let's see how those two events looks in the Venn diagram. Okay, so here is A, here is B. So A and not B. A and not B, again, that's the red area here. B and not A, that's the blue area here. From here, I hope that you notice that those two areas are disjoint. And therefore, according to axiom 3, we can split it into 2. Great. Now, if you remember, we can use now those two properties that we mentioned in class, property number 6 and 7. According to property number 6 and property number 7, we know that the probability of A and not B, even if you don't remember that, by the way, you can always use the Venn diagram. So what is the probability of A and not B? A and not B, that's the red area, so you can take all of A and subtract the intersection. So let's write that. A minus the probability of the intersection. Okay, plus, what is the probability of not A and B? Well, again, that's the blue area, so you can take all of B and subtract the middle part. So plus the probability of B minus the intersection. Great. So we have everything here in order to solve this question. So we have probability of A, the probability of B, and of course probability of the intersection that we computed from the previous section. So if you plug those numbers, you get 0.6 minus 0.4 plus 0.7 minus again 0.4. In the end, the answer that you'll get is 0.5. Okay, that's one way to solve that. Another way, I'll show you in a few seconds. Okay, so way number 2. So I think I can solve it here. It's even easier than way number 1, but you need to understand from the Venn diagram how exactly you can get those two events. So one way is to say, okay, so we want the red area and add to it the blue area. So maybe what we can do is to take all of the area here that includes the middle part and subtract the middle part. So in the end, that's exactly the same as saying, let's take the union of A and B and subtract the intersection. And that's exactly 0.9 minus 0.4, and that equals to 0.5. So it's easier, but of course, you need to think about it in order to get this solution. Okay, now I'd like to show you two different types of sample space. And it's really important that you understand the difference between those two because you'll need to use different formulas for each case. Okay, so one, that's what we call the symmetric sample space. So another way to say that, it's a uniform sample space. So what do we mean by a uniform sample space or symmetric sample space? So basically the definition says that every sample point has the same probability to occur. Okay, let's see if we know already a few examples here. So of course, yes. So I hope that The classics one you already remember. So for example, rolling a die, or even two dice, even tossing a coin, or two coins. Okay, those two classic examples. When we talk about the sample space, the type of the sample space is what we call a uniform sample space, because the probability to get 1 or 2 or 3 or 4 or 5 or 6, exactly the same probability. Okay, so in this case, this type of sample space, how do we solve questions in general? How do we compute probabilities? So in this case, if I want to compute the probability of an event, I need to compute the cardinality of A, meaning how many elements do we have in A over the cardinality of omega. So let me show you an example, an easy one. Okay, so here's an example. Suppose that you're rolling a die, and we define A to be an even outcome. And I ask you, what is the probability of A? So according to this formula, in order to compute the probability of A, I need to ask myself, what is the cardinality of A? Now, an even outcome, what do we have in A? If we write A explicitly, that's 2, 4, and 6, meaning that the cardinality of A equals to 3. So according to the formula, that's 3 over the cardinality of the sample space. How many elements do we have in the sample space? All the different possibilities of the experiment, meaning 6. Therefore, the probability of getting an even outcome by rolling a die, that's exactly 1 over 2. Okay, so that's how we compute in general probabilities in a uniform sample space. By the way, to this formula, we can include also all the different formulas and properties that we proved in class, even the axioms. So in any case, if you understand that it's a uniform sample space, you can use the formula, this one, and any formula and properties that we showed in class. Okay, let me give you another example. Suppose that we have a family with 5 children. Now, what is omega in this case? So omega in this case looks like that. I won't write all the different outcomes, but I hope that you understand how you can continue from here. So it's going to be, so suppose that I write every time the gender. So it's going to be female, 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 female. Then it's going to be male, 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 male. And then female, 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 male. And here we need to write all the different outcomes. By the way, if you know some combinatorics, okay, and we won't study in class combinatorics, how many options do we have here? How many outcomes do we have? So the question is, what is the cardinality of omega? Okay, so cardinality of omega is 2 to the power of 5. That's exactly 32 options. So now I hope that you understand why I couldn't write all the different options. Okay, so now let me just explain why it's 2 to the power of 5, but we won't need that in class. So in general, the idea is that we have each time 2 possibilities, or male or female, or male or female, or male or female, or male or female, or male or female. So it's 2 times 2 times 2 times 2 times 2, 2 to the power of 5, 32 options. Okay, so now let's denote A, the event A, to be the children don't have the same gender. What is the probability of A? Okay. Now, here we assume that it's a uniform sample space, meaning that each outcome here has the same probability. And now, if you think about it, there's too many options in this event. Okay, maybe it's easier if you compute the probability of the complement, because the complement says that of A says that they have the same gender. So let's see. So if I want to compute the complement of A says that it's the same gender. Same gender, there are only 2 options. What are the 2 options? All of them are male, or all of them are females. Okay, so it's 2 options. So if I want to compute the probability of the complement of A, that's 2. That's the cardinality of the complement over the cardinality of omega. So it's 2 over 2 to the power of 5. So it's 1 over 2 to the power of 4. Okay, so but unfortunately that wasn't the question. I want to compute the probability of A, not the probability of the complement of A. But from one of the properties that we mentioned in class, we said that the probability of A, that's exactly 1 minus the probability of the complement of A. That means that if you want to compute the probability of A, the only thing that you need to do is take 1 minus 1 over 2 to the power of 4. And that's all. That's all the question. So we saw the first type of sample space. Let's talk about the second one. Well, so the second type is what we call a non-symmetric sample space. So what do we mean by non-symmetric sample space? So here's the definition. So not every sample point has the same probability. So by the way, we saw an example already of a non-symmetric sample space. The example that we saw in class is the example of the 2 stocks. Okay, and we saw exactly how to solve those types of questions. But let me remind you that the only tools that you can use in this specific type of sample space is the formulas that we proved. So the tools here. So the tools are the properties that we proved and the axiom. You can use the formula of the symmetric sample space. Okay, so you can say, for example, be careful with that. So you can say that the probability of A equals to the cardinality of A over the cardinality of omega. That works only and only if the sample space is a symmetric one. Okay, so in this case it won't work, so be careful with that. Okay, and that's all for lecture number 2. See you on lecture 3.